Okay, in the past couple videos we learned about salts being used as essentially sources of what we would normally visualize as conjugate acids or conjugate bases. We are going to use that information and what we knew from the previous chapter to talk about buffers. A buffer is essentially a solution made from a weak acid and its conjugate base. You can also use a weak base and its conjugate acid. Either way works, but honestly in textbooks and like sampling and stuff like that, they tend to talk about the acid and its conjugate base more often. The reason we would care about buffers is that basically they are able to withstand pH changes. So what you have is this solution that when you add acid to it, it reacts with a conjugate base. And when you add base to it, it reacts with a conjugate acid, and it kind of neutralizes things so it can withstand pH changes. So, for example, suppose we had a solution, or suppose we had this equilibrium, CH3COOH. I mean, we've kind of beaten this one to death, but you know, we've seen it 100 times. This is an acid, a weak acid, and its conjugate base is acetate. We've seen problems where we started with just this, we've seen problems where we started with just this. A buffer is essentially what happens when you have both of them. So if we had, I don't know, a 1.00 molar of this and 1.00 molar of this, what's going to happen is that this can neutralize any base that's added, and this can neutralize any acid because it's a weak base. Now obviously these things cannot withstand a huge pH change. Eventually, you know, if you keep adding base, all of this will get reacted and it won't withstand the pH change anymore. But for at least limited ranges, it can withstand pH changes. And typically, the higher these concentrations, the closer they are together, the better this can act as a buffer. But the higher the concentrations, the more pH change it can withstand. Okay, there is honestly like a nice little algebra equation to explain how buffers work. We're gonna just start with that. This is known as the Henderson-Hasselbalch equation. Okay. I don't know if that's two guys or one guy with a hyphenated name or a girl. I don't know. I have no idea. But the equation is this. The pH of a buffer, so this only works for buffers. If it's not a buffer, this equation is completely useless and you can't use it. Okay, but buffers come up a lot, so we probably should learn this one. pH equals the pKa of the weak acid, so the negative log of the Ka value, plus the log of the concentration of conjugate base divided by the concentration of weak acid. Okay? So, we're going to use this equation quite a bit, actually. As for everything else we've seen in the acid-base chapters, every time there is an acid equation, there is a corresponding base equation. I will tell you that when I was in Biochem 3 in college, we had a problem on an exam that required the Henderson-Hasselbalch equation, but it was about bases, and we had never seen the other equation. And I kind of just did this. I was like, oh, if that's pH, this should be POH. If that's pKa, this should be pKb. And if that's conjugate base on top, I'll make it conjugate acid. And if it's weak acid on bottom, I'll make it weak base. I kind of literally derived this in the middle of an exam by kind of guessing a little bit. And it turned out to be exactly right. So I'm just going to teach it to you now. It's the exact same thing. So if you have a base, you use Kb instead of Ka, so you take the pKb, and it's the concentration of conjugate acid over weak base, and you solve for POH instead of pH. Okay? these two equations will come up all the time. So let's try an example and see how this works. Okay. So what we want to know is what is the pH of a buffer? Well, literally, let's do this one where we have 1 molar of this and 1 molar of this. Okay, pH of a buffer with the concentration of CH3COOH, which is our weak acid, is 1.00 molar. That's acetic acid. And sodium acetate, which is our source of conjugate base, is equal to 1.00 molar. Okay, so that's the weak acid, that's the conjugate base. And we want to know what's the pH. The Ka of CH3COOH is equal to 1.8 times 10 to the negative fifth. I know I keep reusing this one, you probably got that one memorized by now. Okay, well we want to know what's the pH of this buffer. Okay, so we have that equation. pH equals pKa plus the log of concentration of conjugate base divided by the concentration of weak acid. Well, just plug everything in, honestly. So, pH is what we're solving for, so we don't even have to rearrange anything. pKa we can get. pKa is the negative log of Ka. And we have Ka, so I'm going to plug that in. Negative log of 1.8 times 10 to the negative fifth. Okay, and if you plug that in a calculator, it comes out to 4.74. Okay, and then essentially both of these are 1s, but this is our conjugate base, its concentration is 1.00. This is our acid, it's 1.00. And so 1 divided by 1 is 1, and if you take the log of 1, you get 0, which means for this particular problem, this whole part cancels out. All of that cancels out and becomes 0. So for this particular problem, the pH equals the pKa, which happens to be 4.74. So in other words, if you had acetic acid, sodium acetate buffer, and you had equal concentrations of these, the pH will be equal to the pKa, which is 4.74. So mildly acidic, 4.74 is, less than 7. But this is always going to be true, so I guess I'll put a little note here. If the concentration of weak acid equals the concentration of conjugate base, the pH will always equal the pKa. Now, let's try one where they're not the same, just so that you don't think that this is like the answer every time. Okay? Or let's try one where we need to solve for something besides pH. Okay? So we want to know what concentration of sodium acetate, we'll just use the same system, I guess, would be needed to make a buffer with a pH equal to 5.00 if the concentration of vinegar, there's acetic acid, is 0.725 molar. Okay, and we know that the Ka of acetic acid is 1.8 times 10 to the negative fifth. Okay, so this one might be a little more difficult, but conceptually, we know that if these two values were the same, our pH would be 4.78, because that's what happened up here. They were the same. They're not exactly the same because we need something close to pKa, but not exactly. So since we're shooting for a value that's slightly higher than the pKa, we're probably going to need slightly more of the base than the acid. So this is 0.725. Without even plugging any numbers in, we should probably expect a number somewhat bigger. Okay? Probably not like 50 times bigger, but you know, at least a little bit bigger. So let's plug in our values. pH equals pKa plus the log of the concentration of conjugate base times divided by the concentration of weak acid. Okay, well, we literally just did this, but the pKa is 4.74 and the pH is 5. The hard part honestly on these problems is making sure you know which one's the weak acid and which one's the conjugate base. This thing has a Ka value, which means it's the acid. So essentially this is 5, this is 4.74 because it's the negative log of this. Conjugate base is the one we don't know, and the weak acid is the one that's 0.725. So I guess I'll write all that in again just so that you know what we're solving for here. So this is 5.00 equals 4.74 plus the log of conjugate base is what we're solving for. I'm just going to write that as an x, and this is 0.725. Okay, the algebra here. Basically, we got to get rid of this logarithm, but we got to get rid of this first. So I'm going to subtract 4.74 off of both sides. So this cancels out, and this becomes 0.26. Okay, kind of running out of space, but we'll make it work. 0.26 equals the log of x over 0.725. Now we need to get rid of the logarithm. As we've seen on calculators, if you have a log, the secondary function is 10 to the x. I'm trying to figure out how to make that show up a little better. 10 to the x. So we basically need to make all of this an exponent of 10 on both sides. On this side, that makes that cancel out, but this is 10 to the 0.26. So I guess I'll rewrite this. I'm kind of running out of space. Sorry, we'll move it up here. So 10 to the 0.26, help if I don't change the numbers here, equals x over 0.725. So we're literally just multiplying 0.725 to both sides. So x is equal to 0.725 times 10 to the 0.26. Okay? If you plug all that in, the answer comes out to 1.32 molar. So what this means is if we started with 0.725 molar of acetic acid and we added 1.32 molar of sodium acetate, which is the conjugate base, we would still have a buffer because we have the weak acid and its conjugate base. And because these things aren't equal, it's not going to be equal to 4.74, the increase in base is going to give us a pH that is slightly higher. Okay? So in other words, this would tell us how to make a buffer with a pH of 5. We need 0.725 of that and 1.32 of that. Okay? All right, thanks.